Hello, children. I hope you all are in a good state of health and you all are working sincerely to move ahead. So, we are going to proceed with the second video on the concept work, energy, and power. So, let's work on it. In the previous video, we discussed about various forms of energies and their conversions. So, in this video, we are going to work specifically on mechanical energy, that is, potential energy and kinetic energy. Mechanical energy and its different forms. The energy possessed by a body due to its state of rest or of motion is called mechanical energy. It is of two types, that is potential energy and kinetic energy. So first of all, we will be talking about potential energy. The energy possessed by a body at rest due to its position or size and shape is called potential energy. It is denoted by capital U. Potential energy is of two types, gravitational potential energy and elastic potential energy. The potential energy possessed by a body due to the force of attraction of Earth on it is called its gravitational potential energy. Each body experiences a force of attraction due to Earth, which is called the force of due to gravity or weight of the body. The gravitational potential energy of the body is zero when it is at infinity because the force of attraction of Earth on the body is then zero. The gravitational potential energy of a body at a point is the amount of work done by the force of attraction of Earth in bringing that body from infinity to that point. Since work is done by the force of gravity itself, so at a finite distance from Earth, the gravitational potential energy of the body is negative. As the distance of a body from the surface of Earth increases, the force of attraction of Earth decreases and its gravitational potential energy increases. So, the expression for gravitational potential energy is given by U is equal to mgh. So let us suppose a body of mass m lifted from ground to a vertical height h. The least upward force required to lift the body, it must be equal to the force of gravity. That is, F should be equal to G and M, that is product of mass and gravity. The work done W on the body to lift a body to a height h will be given by W is equal to mgh. So this work is done in lifting the body up and it gets stored in the body in the form of its gravitational potential energy at a height h and will be given by U is equal to mgh. When a body of mass m is taken up from a height h1 to a height h2 above the ground, that is h2 is greater than h1, the gain in potential energy will be given by mg into h2 minus h1. But if a body of mass m falls down from a height h1 to height h2 above the ground, the loss in potential energy will be given by mg into h1 minus h2. Elastic potential energy. When an external force is applied on a non-rigid body, it gets deformed due to change in its size and shape. On removal of the force, it regains its original form due to the property of elasticity. Some work is done by the external force in deforming the body. This work is stored in the body in the form of its elastic potential energy. So we can say that it is the amount of work done in deforming the body. So next we are going to start with kinetic energy. The energy possessed by a body due to its state of motion is called its kinetic energy. It is usually denoted by the symbol K. So we have so many examples from our surrounding. It may be car in motion, moving hands of a clock, the bullet fired from a gun, and so on. In this clip, we are going to work on the expression for the kinetic energy. We have been using this expression since class 7th or 8th, but we are actually not aware how we got this expression, how it has been derived. So let's work on it. The kinetic energy possessed by a moving body is equal to the amount of work which the moving body can do before coming to rest. It can be calculated by the amount of work done by an opposing force to stop the body. Suppose a body of mass m is moving with a velocity v. It is brought to rest by applying a constant opposing force F. Let A be the uniform retardation produced by the opposing force, and the body travels a distance s before coming to rest. Then the retarding force F will be given by product of mass and retardation, that is F is equal to m into A. The kinetic energy of the body is actually equal to the amount of work done by the retarding force in making that body move through a distance s before stopping it. That is, the kinetic energy K is equal to retarding force F into displacement s. Now to calculate the displacement s, we have initial velocity, that is v. So children, don't get confused here about u or v. We are actually showing here that the body is already in motion. Since it is already in motion, that's why we are assuming it to be moving with velocity v. So here the final velocity is 0 since the body comes to rest. Since A is retardation, so acceleration A will now become minus A. So from the expression v square minus u square is equal to 2as, if we substitute the values, that is u is equal to v and v is equal to 0, we get displacement s is equal to v square upon 2a. Now if we substitute the values of f and s from equations 1, 3, in equation 2 we get kinetic energy equal to F into S, and if we substitute the values of F and S, we get K is equal to ma into v square upon 2a, that is half mv square. So we get an expression kinetic energy is equal to half into product of mass into square of velocity. So the kinetic energy of the body depends upon square of its velocity of motion. On doubling the velocity of a body, its kinetic energy becomes 4 times. So in other words, we can say a faster moving body has more kinetic energy than a slow moving body of same mass. The next topic that we are going to discuss is relationship between kinetic energy and momentum. So kids, if you remember what is momentum or linear momentum. Linear momentum is given by product of mass and velocity of a body. So let's assume that m is the mass of the body and v is the velocity. Then kinetic energy will be given by half mv square and momentum will be given by m into v. So if I substitute the value of v from the expression of momentum, I'll be getting K is equal to half into m into. So substituting the value of v from momentum, I'll be getting P upon m whole square, which comes out to be P square upon 2m. So I'll be getting square of momentum is equal to twice into product of mass into kinetic energy. Or I can say kinetic energy and momentum are related as P is equal to square root of 2mk or K is equal to P square upon 2m. Now if a light body A of mass m and a heavy body B of mass capital M, and they both have the same momentum, then kinetic energy of light body A will be more than that of heavy body B. And if a light body A of mass small m and a heavy body B of mass capital M have the same kinetic energy, then the body, that is heavy body B, will have more momentum than light body A. So next is now work energy theorem, and it's supposed to be a very important topic. But what is work energy theorem? According to work energy theorem, the work done by a force on a moving body in the same direction is equal to the increase in its kinetic energy. When a force is applied in the direction of motion of a body, it accelerates the motion and thus increases the kinetic energy of the body. This increase in kinetic energy is equal to the work done by the force on the body. So let's again assume that mass of the body is small m with initial velocity small u. When a constant force F is applied on the body along its direction of motion, it produces an acceleration small a, and the velocity of the body changes from u to v in moving a distance s. Now force is given by product of mass and acceleration, and work done is given by product of force and displacement. So we have relation from the three equations of motion. One of the equation is v square minus u square is equal to 2as. And suppose I calculate the value of displacement, I'll be getting s is equal to v square minus u square upon 2a. Now let me substitute the value of displacement in the equation where I have written the formula of work done, that is W is equal to Fs. So what I will get? W is equal to, I'll substitute the value of force, that is Ma, into v square minus u square upon 2a. And a and a will cancel out, so I'll be getting W is equal to half mv into v square minus u square. Again separating, I'll be getting W is equal to half mv square minus half mu square, where half mv square represents final kinetic energy and half mu square represents initial kinetic energy. So if you check out, the expression comes out to be W is equal to kf minus ki, where kf stands for final kinetic energy and ki stands for initial kinetic energy. So I can say that work done on the body is actually increase in the kinetic energy. Now in this clip, we will be discussing about forms of kinetic energy. A body can have three types of motions, namely the translational motion, rotational motion, and vibrational motion. So, the kinetic energy is also of three forms: translational kinetic energy, rotational kinetic energy, and vibrational kinetic energy. So, the very first that we are going to discuss is translational kinetic energy. The motion of a body in a straight line path is called the translational motion, and the kinetic energy of the body due to motion in a straight line is called the translational kinetic energy. For example, a car moving in a straight path, a freely falling body, a molecule of monoatomic gas, they all possesses translational kinetic energy. So the next is rotational kinetic energy. If a body rotates about an axis, the motion is called the rotational motion, and the kinetic energy of the body due to rotational motion is called the rotational kinetic energy, or simply the rotational energy. For example, a spinning top, a rotating wheel, and a rotating fan, they have the rotational kinetic energy. Now the last one is vibrational kinetic energy. If a body moves to and fro about its mean position, the motion is called the vibrational motion, and the kinetic energy of the body due to its vibrational motion is called vibrational kinetic energy, or simply the vibrational energy. For example, a wire clamped at both the ends when struck in the middle vibrates. The energy possessed by the wire is the vibrational kinetic energy. And we have so many examples from our daily life. Conversion of potential energy into kinetic energy. Potential energy changes into kinetic energy whenever it is put to use. For example, a stone at a height has the gravitational potential energy, which is equal to work done in moving the stone to that height against the force due to gravity on it. When the stone is made to fall on a nail standing on a wooden piece, the nail begins to penetrate. The reason is that as the stone starts falling, its potential energy begins to change into its kinetic energy. The falling stone now has both potential and kinetic energy. When it strikes the nail, stone does work on the nail. The kinetic energy of the stone changes into the kinetic energy of the nail, due to which the nail moves into the wooden piece. The second example, as you can see here, is regarding a compressed spring. A compressed spring has the elastic potential energy due to its compressed state. When it is released, the potential energy of the spring changes into the kinetic energy, which changes the ball placed on it and changes into the kinetic energy of the ball, due to which it flies away. We have various other examples, like we have a wound up watch spring has the elastic potential energy which is equal to the work done in bringing it to wound up state. As the spring unwinds itself, the potential energy stored in it changes into the kinetic energy, which does bring work in moving the hands of the watch and thus changes into the kinetic energy of the hands. Same way, you must have seen the string of a bow when you pull it. Some work is done which is stored in the deformed state of the bow in the form of its elastic potential energy. On releasing the string to shoot an arrow, the potential energy of the bow changes into the kinetic energy of the arrow, which makes it move.